In this video, we are going to be discussing electric and magnetic potentials. Now, electric potentials are things that we have seen before in this course. In fact, we've already used the definition of the electrostatic potential, V. However, there is also a magnetic potential. And as we'll find out later on, these potentials are actually a little bit more of a mathematical convenience than anything physical, which means that we can make certain choices as to how we define these potentials. So just as a warning, this episode is going to be a little bit more abstract than maybe some of you guys would be used to. And in fact, gauge transformations are something that I struggle to understand until I thought of it as essentially something that was a mathematical convenience. So without further ado, let's go ahead and dive right into it. So as we've seen many times in this lecture series, we've used the definition that the electric field is equal to minus the gradient of the potential, V, right here. And this formula right here enabled us to say if we knew the electric field of a point charge, which we said many times has been equal to Q divided by 4 pi epsilon naught r squared, we could then essentially integrate this electric field to give us the value of the electric potential right here. And so to do that, we essentially reverse this equation to give that V is equal to minus the integral of E dot dr right here. And so when you substitute this in and you work out all of the dot products and you use symmetry arguments to say there is only a radial component, then you get that V is equal to Q divided by 4 pi epsilon 0 r, which is the familiar expression for the electrostatic potential of a point charge in space. So that's all well and good. But we also know that from Gauss's law, which is Maxwell's first equation, that the divergence of E is equal to rho divided by epsilon. And for now, we're going to assume that we are in free space. So we can essentially combine this equation with this equation to substitute in what E is right here and write Gauss's law in terms of the electric potential as opposed to the electric field. And so when we do that, we get the divergence of minus the gradient of the potential is equal to rho divided by epsilon naught. And so whenever you have a divergence of the gradient, this is the Laplacian of the potential. And this is going to be equal to minus, just bringing the minus sign over on this side, rho divided by epsilon 0. And this right here is known as Poisson's equation. And it's telling you that if you differentiate the potential twice, this equates to a charge in free space right here. Now, there is actually a special case of this equation where this right-hand side is equal to 0. And this is the case when there is no free charge in all of space. So when rho is equal to 0, then obviously this right-hand side is going to be equal to 0. And so we get the equation that grad squared of V is equal to 0 right here. And this is what's known as Laplace's equation right here. And this is a special case of Poisson's equation. But Laplace's equation is essentially a way of determining what the potential is in a region of space given various boundary conditions. Now, to solve this equation, since it's a differential equation, you need to know boundary conditions. And so you need to know what the potential is at certain positions in space. But essentially, you solve this equation to figure out what the potential is in each region of space. So just to illustrate how to solve this equation, say if you have a problem, because this is the sort of thing that can come up a lot on exam problems. So let's say we are in spherical coordinates right here. Then how would we solve this equation in spherical coordinates? Well, this is at the point where you look at the identities table and you find that the Laplacian in spherical coordinates is equal to 1 over r squared times d by dr times r squared dv by dr. Now, there is actually a theta component and a phi component, because of course in spherical geometry you have r, theta and phi. However, for this example, we're just going to assume that the potential is spherically symmetric, which is probably the most physically accurate scenario you're going to be dealing with. And so therefore, this is equal to 0. So this is just the example in spherical coordinates. So from this equation, you can actually just essentially get rid of this 1 over r squared and write d by dr r squared dv by dr is also equal to 0 right here. Now, when you integrate both sides, this is where you have to be a little bit careful when adding plus c's and stuff. So if the derivative of this term is equal to 0, then this term on its own will essentially equate to a constant, so something that doesn't depend on the radial coordinate right here. Because when you differentiate this, you get 0, which is what this equation is telling us. So now we can divide both sides by r squared and get dv by dr is equal to c divided by r squared right here. But we still have one more derivative, and so if we integrate this again, we get that v is equal to minus c over r, because when you integrate 1 over r squared, you get minus 1 over r, plus another constant, which we'll just call c prime for now. So this right here is the most general form of the electric potential in spherical coordinates. And this, although we don't have any sort of boundary conditions, this actually reflects what the electric potential of a point charge is, which is q over 4 pi epsilon 0 r in free space. Now, obviously, this only gives you the functional form, but you essentially get this 1 over r dependence right here, and that is what's reflected in this equation right here. And so, although you have to apply a bunch of boundary conditions and some actual physics, in terms of just pure mathematics, this just solving Laplace's equation does actually give you the correct dependence of the potential on the radial coordinate right here. So that is the solution of Laplace's equation in spherical coordinates, but of course the geometry very much matters, because I'm going to now solve it for cylindrical coordinates. So we said the Laplacian of the potential is equal to 0 for Laplace's equation. But let's apply this now for the cylindrical case. And for this example, we are going to assume that the system has cylindrical symmetry. And what we mean by that is, like with the spherical case, the value of the potential only depends on the radial coordinate. So for that, when we look up what the Laplacian is in cylindrical coordinates, we get 1 over r d by dr into r dv by dr is equal to 0. So remember, this is the Laplacian equation in cylindrical coordinates rather than spherical. So let's go ahead and solve this in a similar way. So we're going to get d by dr of r dv by dr is equal to 0. Integrating this the first time, we're going to get r dv by dr is equal to a constant right here. And we divide this by r, so we're going to get dv dr is equal to c divided by r. And then when we integrate both sides of this equation, we're going to get the potential is actually, well, when we integrate 1 over r, we're going to get a log function, a natural log of r right here, which is what happens when we integrate 1 over r, and we're going to get a second constant right here, just like with the cylindrical case. So as you can see, it depends on the geometry of the system. So a system with cylindrical geometry will have a different form of a potential as a system which has spherical geometry. Now, if you remember back in the video I did on electrostatics, we actually found that the electric field of a sort of infinite line of charge right here is equal to lambda divided by 2 pi epsilon 0 r, where lambda is equal to the charge per unit length. And this was in the radial component. And so we can actually see that if we integrate this equation to get the potential, because of course E is equal to minus the gradient of the potential, then, well, we have a 1 over r, and when we integrate that, we're going to get a log function. So this, again, confirms what would be happening in the cylindrical case right here. So this is kind of a different approach to electrostatics, and that's why I kind of mentioned that this is going to be a more mathematical video, because this is focusing a little bit more on the mathematical ways in which you can solve various electrostatics problems right here. So what about for the magnetic case? How does this apply for the magnetic case where everything in magnetism is similar but slightly different? Well, we know that in magnetism, we have the equivalent of Gauss's law is Ampere's law. And for now, we're just going to use the basic form of Ampere's law, where curl B is equal to mu naught J right here. And the other equation is that the divergence of B is equal to 0 right here. So these are our equations of magnetostatics. So this is where the current is constant. Now, we said that the equivalent of Gauss's law in magnetism was essentially this equation right here, Ampere's law, because this says that if we have a field, then we have some kind of density right here, some current density, which is similar to Gauss's law. Now, if the current is 0 right here, and I know that this is a bit of a bad assumption to make, but there is a reason why I am making this, then we can actually say that from that the curl of B is also equal to 0 right here. And therefore, if the curl of B is equal to 0, then we can actually say that the B is equal to minus the gradient of some other potential right here, because curl of the gradient of any scalar, psi, we'll just say that for now, is always equal to 0. This is a vector identity. This is a mathematical identity. So therefore, we can define B in terms of a minus the gradient of a magnetic potential right here. And to keep the units right, we will just multiply it by mu naught, so that when we take the curl of B, then we get mu naught J. So if we assume that the current density is 0 right here, then we have this magnetic potential right here. And also we can say that the divergence of B is equal to 0. And so therefore, if we insert our form for B right here, we get minus mu naught times the divergence of the gradient of the magnetic potential is equal to 0 as well. And so therefore, the Laplacian of this potential is equal to 0. So therefore, we have another Laplace equation. However, all of this is pretty useless because we've just assumed that J is equal to 0. So that pretty much makes this magnetic scalar potential entirely useless right here. So in electromagnetism, we hardly ever talk about this potential term right here. And what we actually do is, rather than defining a scalar potential, we actually define a vector potential. So how are we going to define this? Well, let's go ahead and consider this equation right here. The divergence of B is equal to 0, which is Maxwell's second law, saying that there is no magnetic monopoles. Now, a vector identity that we've been using is that the divergence of the curl of any vector right here is equal to 0. And this is true for any single vector A right here. And we've actually been using this identity a few times before. So given this, it seems pretty logical that due to the fact that this is always true and this is always true, we can just define B is equal to the curl of this A vector right here. And this A term right here is known as the magnetic vector potential. And this is generally what we use in electromagnetism when trying to characterize magnetic potentials. We use this A term right here, and this is a vector potential. And so if you know what the magnetic field is, you can therefore derive what the potential is by essentially integrating it and setting boundary conditions. Now, here is the key thing. This A term right here is not uniquely defined, and this is a really, really important point. You can actually have an infinite number of mathematical functions A right here that essentially lead to the same result for B right here. And this is a really important point to note. As long as when you take the curl of this A right here, you get the correct value for the magnetic field, which of course is uniquely defined, then you essentially can choose whatever equation for A, because there is actually a lot of different ways you can get the same end result when you take curl of a function right here. And so this actually gives you a little bit of freedom. Whenever you have freedom, you actually have to adopt a certain convention. And the convention that for now we are going to adopt is that we are going to say that whenever we take the divergence of this A right here, we're going to say that this has to equal 0. So this actually enables this A vector to be uniquely defined. And this just helps us to solve the equations most easily. And this right here is known as the Coulomb gauge right here. And so this choice, this kind of what might seem like an arbitrary choice, is called a gauge right here. This is what's known as a gauge. And this kind of equation right here is just called the Coulomb gauge. And as we'll see a little bit later on, there are in fact other gauges that we can choose to help us solve our electromagnetic problems. So let's go back to Ampere's law, which is the curl of B is equal to mu naught J right here. Well, now that we have a form for the magnetic potential, we can rewrite this in terms of the magnetic potential to get that the curl of A is equal to mu naught J. And like we've done a few times in past videos, we can transform this curl of curl into this equation right here. But since we said that the divergence of A is equal to 0 in the Coulomb gauge, then we can write just the Laplacian of this vector right here is equal to mu naught J right here. And so we have this result, which is pretty much what we got for the electric case, where we of course had the Laplacian of a potential is equal to a density right here. And that was made possible by the fact that we chose this term right here to be equal to 0. This divergence of A is equal to 0. And so this right here is another Poisson equation. Now let's go ahead and see if we can solve this Poisson equation in the case of a current carrying wire right here. So let's go ahead and draw out what we have. So we have a wire which is carrying a current right here, and we are going to see what we get when we solve this equation right here. Now in contrast to the electric case, we actually find that the terms on both hand sides of the equation are actually vectors rather than scalars. So we have to think about what components we are actually interested in. Now J is only going to have a Z component, and therefore if J only has a Z component, then that's telling us that the Laplacian of the magnetic vector potential also only has a Z component right here. And so what we can do is we can actually demote this equation into a scalar form and say that del squared of A, but only looking at the Z component, is equal to minus mu naught times jz right here. And so what we're going to do is we're now going to substitute in the Laplacian in cylindrical coordinates with our function being az, the Z component of A, because of course we've demoted it to just being the Z component of the magnetic vector potential, because of course that is going to be the only component which is going to be parallel to this J right here. So when we do that, we are going to get this right here. Now this equation of course looks pretty horrible. However, as with the case earlier, we actually know that because we are dealing with a cylindrically symmetric system, that is to say that it doesn't matter what the angle is nor what the Z coordinate is, so how far along the wire, the magnetic field will not change and so therefore the magnetic vector potential will not change either. And so therefore we can just essentially eliminate these two terms right here, because of course they're not going to change with theta nor z. And so rewriting that, we are just going to get this right here. So as with before, let's go ahead and rearrange this. So moving the 1 over r up top, we get this. And we're going to integrate both sides of the equation with respect to r to remove this derivative right here. And when we do that, we get this on the left-hand side. And this is going to be equal to minus mu naught jz times the integral of r dr. Now, of course, this is an indefinite integral. But when we do that, we're just going to get 1/2 times r squared plus a constant term right here. So that's our first integration, and now we can divide both sides by r to remove this r on this left-hand side of the equation. So we get this right here. And now to integrate this equation for a second time with respect to r, we are going to get, for this first term, we're going to get another 1/2 r squared, which will then just multiply to give minus 1/4 times mu naught jz times r squared. That's our first term. And when we integrate this term with respect to r, well, we've got a 1 over r, so that's going to give us a natural log function of r right here. And of course, we're going to get a second constant right here. If we technically do the integration separately, then obviously they will each give separate constants, but we can just add those two constants to get a new constant right here. So there just will be an extra constant term right here, which for the moment we don't really care about. So there we go. This is our form for the magnetic vector potential of the wire. Now, this may look a little bit counterintuitive because, of course, what I said earlier was that the magnetic field is equal to the curl of the magnetic vector potential. And we know that the magnetic field around a current carrying wire as a function of the radial coordinate is equal to mu naught times I divided by 2 pi r. And of course, we said that that was in the theta hat direction as a vector. But it doesn't really look very close to that result whatsoever. So what's going on right here? Well, like I said before, this is a very mathematical exercise. And in order to kind of translate from the mathematics to something a bit more physical, then obviously we have to apply these boundary conditions. But you guys will probably be like, wait, it doesn't really matter what boundary conditions we have. Why is this r squared coming from? Well, it's important to remember that this formula right here applies for any radial coordinate that is outside of the wire. But when we do the exact calculation and apply Ampere's law inside the wire, we actually find that the magnetic field strength is proportional to r right here. And if we look at the first term of this vector potential, this is of course proportional to r squared. And so when we take the derivative of a, which is what we do when we take the curl, we're just taking a whole bunch of derivatives essentially, then yeah, we will get something that's proportional to r if we're starting with something that's proportional to r squared. So this a vector right here is a little bit more complicated. It does require a little bit of physical interpretation because this term right here, this first term, is actually the magnetic vector potential inside the wire. But this second term right here is a log function, and that is of course characterizing the vector potential outside the wire. Because of course when we differentiate log r, then we're obviously going to get something that's proportional to 1 over r, which is our more familiar expression for b anyway, right here. So this is, again, a very generalized form of the magnetic vector potential. And this c term right here is actually just equal to all of the constants of this equation right here, which in this case is mu naught I divided by 2 pi. And of course, this c term right here, anything would apply because, of course, if you differentiate that, then that's just going to disappear essentially because it's not depending on any of the coordinates. And so taking curl will of course just eliminate that c prime term entirely. So that's kind of why maybe this expression doesn't look overly satisfying, and it doesn't immediately look like the expression for the magnetic field outside of the wire. That's because it's essentially got both the inside case and the outside case. But of course, physically, we know that for when it's inside the wire, it's one functional dependence, but when it's outside of the wire, it actually behaves entirely differently, depending on the radial coordinate. So here we go. We have our two equations which essentially characterize both an electric and a magnetic field in terms of a potential function. However, this isn't actually quite the full picture, because of course we've only really used these two equations in time-independent problems. And so, of course, when we have E is equal to minus the gradient of V, then that is going to work very well if we have a point charge and we want to work out the potential. We just do the derivative. But what if the electric field is changing? Will this still apply? And similarly for the magnetic field, this worked of course very well when we had a long current carrying wire carrying a singular current I. However, what if the current is changing? What if it's like in Lenz's law and we have a changing current being caused by a changing magnetic field, where in this case we obviously have a time dependence on our system? Will it still work? The answer is no. And to explore why it doesn't work, we're actually going to use Maxwell's third equation, which says that the curl of E is equal to minus dB by dt right here. So when we do that, we are going to get the curl of minus the gradient of the potential function is going to be equal to minus the time derivative of the magnetic field, which of course we said was the curl of the magnetic vector potential. Now here's the key thing. We have a curl of a gradient of a function. And what did we say happened when we have curl of gradient of any scalar function? This hand side is always going to be equal to 0. Curl of the gradient of any function psi is always going to be equal to 0. That is a mathematical vector identity. And so this hand side of the equation, we get 0, which is then telling us that the time derivative of the curl of A is always going to be 0 right here. And that kind of doesn't really apply very well, because of course when we have a changing current, of course we're going to have a changing magnetic field, and therefore, of course, we're going to have a changing magnetic vector potential. So saying this as it is at the moment is actually not very good. And so the reason why we got this kind of null result on the left-hand side was actually because our equation for E is equal to minus del V, was actually incomplete, and it didn't contain any time dependence right there. And so what we actually need to do is, for this E equals minus the gradient of V, we actually need to add on an extra term which will kind of match whatever's on the right hand side right here. And so how do we get this extra term? Well, let's just go ahead and for now put in any sort of function, which is just going to be like a random function of time, which we kind of don't really know at this point, but we're just going to say that we're just going to add on this extra thing which we know has to depend on time. So let's go ahead and apply Maxwell's third equation yet again. So we get that the curl of E, which of course is now minus the gradient of V plus this function of time, this is equal to minus the time derivative of the curl of the magnetic vector potential A right here. So expanding the left-hand side, well, this first term, of course, is going to be 0 because curl of gradient of any vector is 0, which is what was kind of giving us the problem. But when we expand out the second term, we get the curl of this function f right here is equal to minus d by dt of curl A right here. And what we can simply do is we can actually just switch around curl and the time derivative, because of course curl is a spatial derivative and this is a time derivative, so they are independent things. And so we can get that the curl of f right here is equal to the curl of minus dA by dt right here. And now, of course, we just have curl of two different things. And so if we just remove the curls right here, then we just get that our mystery function f is equal to minus dA by dt right here. And so there we go, we have our mystery function, which we can go ahead and add into the equation for the electric field. And so for time-dependent problems, we get that E is equal to minus the gradient of the potential minus dA by dt right here. And so we have this fixed form, along with, of course, our magnetic field equation, which is, of course, that B is equal to the curl of the magnetic vector potential. So these are our two equations which tell us about the potential, relate the potential, which is, of course, more of a mathematical convenience, really more than anything else, to our physical quantities, which are the electric field and the magnetic field right here. And so what we can do with that is we can actually go ahead and rewrite Maxwell's equations. Instead of in terms of the fields, we can actually write them in terms of the potentials. And so when we do that, we get these two equations right here. And so these new equations essentially contain all of the information within Maxwell's equations. They're just written, instead of the fields, they are written in terms of the potentials. And of course, we said before, we could actually make a choice as to what gauge we're using. So of course we said that within the Coulomb gauge, we had that the divergence of A is equal to 0, and therefore of course this eliminates quite a fair few number of terms. That is this term right here, and of course this term right here. So that would actually enable us to simplify things depending on what system we are dealing with. But of course this isn't going to be true universally right here. Now, as well as the Coulomb gauge, there are two other important gauges that will be useful for solving electromagnetism problems. And one of them is especially tied in with relativity. And I'm not going to necessarily derive what this gauge is, however, I will show how it's important. And this new gauge that I'm talking about is what's known as the Lorentz gauge. So, whereas before we said that the divergence of A is equal to 0, which was able to help us solve various problems, the Lorentz gauge is essentially similar. However, rather than the divergence of A being equal to 0, we are actually going to make the choice of the divergence of A being equal to minus mu naught times epsilon naught times dV by dt right here. Now, what happens when we substitute in this into Gauss's law right here and Ampere's law right here? What are we going to get? Well, for Gauss's law, we are going to get this equation right here. And for Ampere's law, we are going to get this right here. And if we actually have a look at the left-hand sides of these equations right here, we have a del squared, which is of course a Laplacian operator, and therefore it's the double derivative with respect to space term right here. And we have a double derivative with respect to time of the same function right here. So this should kind of remind you guys of a certain type of equation. And yes, you guessed it, this is the wave equation right here. And so we can kind of actually see that if everything on the right-hand side in these two equations is equal to 0, then we are essentially going to get a wave solution for the magnetic vector potential and the electric scalar potential. And the key thing to note with the Lorentz gauge is that these equations are invariant under special relativity, and it doesn't matter how fast you are necessarily moving with respect to the electric and magnetic fields, the result is still going to be the same. So this Lorentz gauge essentially unifies electromagnetism with special relativity, which is really, really cool. And the final gauge, which I was going to mention, is called the Weyl gauge. And this one is quite an easy one. This one essentially says that the electric potential is equal to 0 right here. And so what are we going to get when we find the electric potential being equal to 0? We get these two equations right here. And of course, this actually allows us to be able to write the entire thing in terms of the vector potential A. And this is kind of like a less popular one, but it's still quite commonly used in order to solve some electrostatics problems, simply because it can very easily give you the charge density rho just from the magnetic vector potential, and it kind of puts it all in terms of the magnetic vector potential right here. But typically this one isn't really used as much. Most commonly, you'll be probably using the Coulomb gauge for steady state problems and the Lorentz gauge for problems which require Lorentzian transforms of special relativity. So there we go. I hope that was really helpful. I know that was a very mathematical one, and I will be touching upon gauge theory of transformations later on in the course, particularly when we come and look at radiating dipoles. And that'll probably be one of the last videos in this series. It is probably one of the most advanced topics within all of electromagnetism. But yeah, we will definitely be doing some more physically significant stuff within the next video. So I hope that was really helpful, and I'll see you guys in the next video. Take care.